Thank you, Tushan. And thank you for inviting me to the OpenPOWER Summit North America. The key challenge that I'm trying to address in this work is that as our software gets more complex, it's now getting harder and harder to install our tools and libraries correctly in an integrated and interoperable software stack. To address this issue, I'd like to give a background about the Department of Energy's roadmap to exascale systems and why this is such an important issue. So DOE, as you're aware, is building an impressive productive lineup of accelerated node systems supporting our DOE's mission. And starting from pre-exascale systems in 2012 through 2016, where we had systems like Cori at Berkeley Lab and Summit and Sierra at Oak Ridge National Labs and Livermore, which are our current top HPC systems, you can see that they're built with the OpenPOWER architecture with NVIDIA GPUs. So both Summit and Sierra are based on NVIDIA V100 architecture. And you can see that previous generations as well only had NVIDIA GPUs. Now going into the future, Perlmutter at Berkeley Lab has NVIDIA GPUs, but there are other GPU architectures as well of interest to DOE, including AMD and Intel. And this is the roadmap to exascale systems, where we can see our current Summit and Sierra systems. So our goal is to build a comprehensive, coherent software stack that enables application developers to be very productive and to develop parallel applications that can target these diverse exascale architectures. This is a challenging problem, as you can imagine, in the software technology field of area of ECP. You want to prepare the software stack for scalability with massive on-node parallelism. And we want to extend existing capabilities when possible and then complement the efforts and integrate with the vendor efforts as well to deliver high quality robust products that are vertically integrated. So the software technology area has 6 technical areas, and there's another one on workflows that we are integrating. It encompasses a diverse selection of areas in programming models and runtime in the software development kit. And I lead that effort for the SDK in this PMR area. There's development tools, there's math libraries, there's data and visualization. We have NNSA software technology products and the software ecosystem with E4S. So with these technical areas, our goal is to deliver E4S as a framework that provides better quality software with documentation, test cases, integration with applications, and be able to deliver this on HPC systems where it's easy to build and use. So delivering HPC software to facilities, vendors, agencies, industry, and international partners in a new way. We have defined community policies that you must adhere to if you want to be part of the E4S ecosystem. There is a doc portal that is a single portal to all the E4S product information. There is portfolio testing. We curate a set of packages. We have quarterly releases. We had a last release in August 2021. It's the 21.08. The next release is expected next month at Supercomputing. We have build caches, which hosts binary the packages for different operating systems and architectures. We have a turnkey stack. And we also have a strategy group that I'll talk about a little later. So in short, the extreme scale scientific software stack is a curated Spack-based software distribution. We have binary build caches for bare metal installs, and we target architectures including x86-64, PPC-64LE, and ARM64 as well. We have Docker container images, and we have these images hosted on Docker Hub as well as on E4S website. And these include Docker as well as Singularity images. We have base images so that you can create your own custom image from there. And also we have a full-featured container image with GPU support. So if you were using this on a PPC-64LE platform, you will be able to just use this with support for NVIDIA GPUs, for instance. Now we have recipes for creating custom images starting from base images. We also have integration with continuous integration frameworks, including GitLab. And I'll talk a little bit more about that. So this is a huge effort, but just putting together these packages is not sufficient. We also need a validation test suite. And this test suite allows us to verify that the software we deliver is functioning correctly. For those who want to learn more about E4S and containers in general, we also have a virtual box image that you can just install on your laptops and learn more about Docker, Singularity, Shifter, Charlie Cloud. And there are also images that we have on AWS and Google Cloud Platform. So there are these three areas. ECP is the application development. We have 24 applications spanning a wide range of areas, including national security, energy, earth system, economic security, materials, and data. And then there is the software technology. And then there is hardware and integration, where we deliver the products from E4S to the facilities. So we work on products that applications need now and also look into the future. So as you're aware, MPI is the backbone of HPC applications. And we have two major MPI distributions, including MPICH and OpenMPI. And many of these are integrated in vendor stacks as well. We have OpenMP, OpenACC for on-node parallelism. We have performance portability libraries. And I am referring to packages such as Cocos or Raja that allow you to express parallelism using a lightweight C++ Lambda function, an API for allowing you to express parallelism in the code without specifying what the target architecture is. So you can have a backend of a GPU, you can have a backend that corresponds to pthread or OpenMP from your code and keep a single source code. We have LLVM, and there's a lot of effort that DOE is putting in LLVM compilers. And LLVM compilers are being integrated in the vendor software stacks as well. We have performance evaluation tools, and these include tools such as PAPI for accessing hardware performance counters on the CPU and GPUs, and TAO and HPC toolkit. We have math libraries such as BLAST, sparse solvers, Trilinos, sundials, and they provide scalable algorithms and software, enabling solvers to be deployed on your applications in an easy way. We also have I/O libraries such as Adios2, HDF5, MPI I/O, and data and visualization products, including ParaView and Visit. So this is a broad portfolio of capabilities that have been developed within the DOE and the national labs and universities. And these software technology products are then bundled into group of logically related packages known as SDKs. And then there's different types of SDKs, and they are all integrated within the E4S distribution. Here is the web page of E4S, and you can see that the community policies over here. And these are the community policies that allow a package to be integrated in E4S. They must have a Spack-based build and installation. That is the first and foremost requirement, because Spack is the platform that DOE has embraced as the key way to deliver the software. You need a package manager that is portable across different operating systems, across different platforms, and Spack provides that capability. We need to have a minimal validation test suite so that we can verify that the package does what it claims to do. It can be a smoke test, it can be integrated as a Spack smoke test and then be integrated in the E4S validation test suite, but it needs to have this minimal validation testing. And there's a number of different policies. I will not go into all of these right now, but they're based on the XSDK product that predates the E4S work. You can learn more about it on the E4S webpage. And this is a list of all the packages and releases we have had for E4S. Starting in October 2018, where we had the first release, where we had 24 products in that E4S release. Now we are at 88 full release products, and it's a lot of work to get all these packages working coherently, so that if there is an MPI library such as MPitch that they all target, then it's the same consistent MPitch library that's used across the different products, the same set of compilers, and the operating system is important. So I would say that EFS is a community effort. It's a community effort to provide open source software packages for developing, deploying, and running scientific applications on HPC platforms. Our goal is to deliver a modular, interoperable, and deployable software stack. But that stack is based on the Spack package manager. And we provide both from source builds as well as containers of a broad collection of HPC software packages. And we enable uniform APIs where possible. So I'll say that it exists to accelerate the development and deployment of HPC software so that we lower the barriers for HPC users. E4S provides containers for a number of different packages, including all of these areas like MPI, development tools, math libraries, data, and viz. Now, you may be wondering, why Spack? Why did we choose Spack as the package manager for software delivery? Well, Spack allows you to specify different capabilities. You can specify versions of software packages, for instance. You can use Spack not just for E4S, but for also a large collection of other software tools and libraries outside of our software technology area. And it's a very popular and growing package manager that's being used now on many HPC centers to deploy the full software stack. So the reason for this is that scientific software is getting extremely complex. Here is the dependency graph of packages for a package Nalu. And this is a CFD code. It provides a generalized, unstructured, parallel, massively parallel, low Mach flow. And it's used for products such as Nalu Wind for wind turbine simulation. Now you can see that Nalu depends on Trilinos depends on ParMetis, which depends on Metis, which has these dependencies. And this just complicates the installation when you have so many moving parts. Here is DEAL2, a C++ finite element library. And you can see the complexity of dependencies, whether it is with NetCDF or other packages. Here is another graph for RMiner, R data mining library. And so you get the idea that our software is getting more and more complex. Now, even proprietary codes are often based on any open source libraries. And here you see that half of this directed acyclic graph is blue, and more than half of it is open source packages. All of these packages are open source, and nearly all of it needs to be built specifically for HPC to get the best performance. So we're building an entire ecosystem of 15 or more applications where we have 80 different software packages. And there are 5 target architectures and platforms. There are multiple compilers, including the IBM Excel compilers, the GCC compilers, the Clang compilers. We're looking at different programming models as well for inter and intra-node parallelism. There are multiple versions of each package as well. And so this leads to a combinatorial explosion of the number of options that a user has to contend with. How do you name this complexity? Because every application has its own stack of dependencies, and it has gotten to a point where many users and utilities dedicating several FTEs to just building and porting libraries. And there has to be a better way. We often trade reuse and usability for performance. So we need to make it easier to rely on other software. But how do you install software on a supercomputer? Well, you start by downloading all the 16 tarballs that you may need in your application. And then you start building. And the user, the poor user, is faced with this issue of getting all the options just right. You have 16 different builds that you have to deal with. You configure, you make, you fight with the compiler, you tweak the configure arguments, you again fight with the configure scripts, make it. And once you get all of these assembled, then you run your application, which depends on all these different packages, and then it segfaults. And then you start all over again. And it's a very frustrating process where it's very hard to manage. Now, you may say, well, what about modules? Well, modules just set paths to packages that somebody else has already installed. So someone in your HPC center has already installed the compiler, the runtime, and all the other things that make up the modules. So you need a better way to handle this complexity. And Spack is a flexible package manager for HPC. To use Spack, all you need to do is just clone like this. You say git clone, and then you set up using a setup environment script, and then you are ready to install a package. You could say Spack install tau, and the tau performance system and its dependencies are then installed within the Spack directory structure. But what is interesting about Spack is that it can also install many variants of the same package, and they can coexist. You can have support different compilers, different MPI implementations, even different build options. So you clone Spack and you set up, you can say Spack compiler find, and then it finds the compilers in your path. So if you have loaded Intel compilers or GCC or Clang compilers, it recognizes those. You can also say Spack external find, and I highly recommend this command because then it does not need to install the dependencies from a scratch, from source code. You can just say Spack external find, and packages like AutoConf, CMake, or M4, they are all found in your environment, and it recognizes that it can use those instead of downloading, for instance, the source code of CMake and trying to compile it from scratch. Now, once you are set up with the Spack environment, you can just say Spack install tau, and then it will install a version of tau. Or you can specify with @ symbol a custom version. So you could say, please install tau version 2.30.2, and it will then download that version. It also understands compilers. So you could say %GCC 730, and then it will used the GCC compiler, which it had found in the Spack compiler find with version 7.3.0 to install tau. You can also specify variants for a recipe for a spec. So you can say plus MPI, Python, pthreads, and then these build options are enabled for tau. You can specify an MPI, and the MPI is provided by MVAP H2 version 2.3, which has a variant called wrapper RPath, which is disabled with the tilde option. So you can go in detail and specify dependency information about who provides a particular capability. So this spec syntax is recursive. Now we use it to build a number of these packages, and you can see over here all of these packages built for the Power 9 PPC64LE architectures. You can just say Spack find and it will show you the different packages. Then you can say Spack load and it will load that. So Spack simplifies HPC software for users, developers. You can learn more about it at spack.io. And Spack is central to ECP's software strategy. So with this, we are building all of the E4S products across the different areas, such as programming models and runtime, compilers and support with LLVM, tools and technology, which includes tau, HPC toolkit, XSDK or the math libraries, visualization products like ParaView, Ascent, Visit, data management and iOS libraries, including HDF5, ParallelNet CDF, and then there are other packages that you can see over here across different SDKs. So with this, we are able to create binaries and install them with bare metal installations and also support custom container builds. We've had a recent release, as I mentioned, 21.08. And here we have a recipe where you can just download this. You can point to a build cache and say Spack mirror add E4S, and then point to this cache.e4s.io for a particular version, and then accept the keys. And then when you say Spack install HDF5, it will not download the source code if it matches the keys, the hashes, and it will just download the binaries that are there in our binary build cache. So this simplifies this deployment of software tremendously, because you're not fighting with the compilers and tweaking these configure arguments. You have a well-tested software installation. You can also download a container. Now we support Docker and Singularity containers. You can see over here, there's a PPC64LE option, and you can just get this container, a single file, and it will be productive with its use with Singularity as the only dependency. Or if you have access to a system which has Docker or Podman, you can say Docker pull and then do the name of this image like this. We also have other images on PPC64LE. These are images spanning Red Hat Enterprise Linux 7, 8, which comes from UBI, and Ubuntu images as well. You can start with these images. You can start with these images and create your own custom image. And then here are the distributions on Docker Hub, where you can just do a Docker pull command like this. So what all do we include for the OpenPOWER platform, which is relevant here in today's workshop? We have 88 different products. These span a number of different areas. Now you can see over here the exact path in our Singularity image. We have Adios to Axon, we have tools Gasnet, Ginkgo, HDF5, Cocos for node level parallelism. We have MPitch. We have tools like ParaView, Ninja, scalable checkpoint restart, SCR, Strumpack, Sundials, SuperLU, Tau, Trilinos. And by Trilinos, I mean there are probably 70 or more libraries that are in the Trilinos installation, which spans a range of different solvers. And you get the idea. There are 88 different packages that may be immediately useful for your HPC application deployment. We also have support for LLVM, the DOE fork of LLVM, which tracks the upstream. So you have Clang 13 support. You can see a number of packages that have been built with LLVM. So we also have GCC, LLVM, and other vendor compilers support. So here you can see MPage, you can see tools like Turbine, VTKM, and these are built with LLVM for PPC64 LE. We have GPU support, and you can see over here that this is a version 1.2, where I can just say import TensorFlow, PyTorch, OpenCV, Matplotlib, NumPy. If I say TensorFlow test is the GPU available, I can see the 4 V100 GPUs listed over here. So this allows me to just immediately install one particular package, the Singularity image, and run it like this, and then it will get access to all the GPU runtimes. These are the base container images for Ubuntu, Red Hat, and CentOS. And we have support for multiple architectures, and these are Docker images. Now here is an example where you can start from a Docker image that's provided by ECP, E4S. And then based on this, you can copy the spack.yaml file and then run this command, which is saying spack install, but use the cache. So now we are getting the packages from the binary build cache, and then specifying the work directory to build these Docker images. And these are Docker images for different architectures, as I mentioned before. And there's a spack.yaml file. This describes the environment to the Spack system. You can have a bare metal install where you can just say, in the directory where spack.yaml file resides, you can say spack-e dot for the current directory install. Or you can use a Docker file like this, where you can have a Docker build, and it will pick up the Docker file, and then it will use the Spack. Now, you may be wondering what architectures and what operating systems do we support for the build cache? And this is the page at the University of Oregon, at the oss.uoregon.edu/E4S, where we have over 50,000 Spack binary packages. And then the key advantage to this is that if your architecture operating system compiler matches with the Spack version, and this is the hash of the concretizer, then it can pick up the binary from here without requiring to rebuild. That can be a great advantage across different operating systems and platforms, where you have the same package manager that can be used. Here is an example of the WDM app, the whole device modeling application for the ITER fusion reactor. And then you can see how the images can be used to create Docker containers and how you can use it for the installation. There's another project called Pantheon, and they are reporting a 10x speed up in the use of the build caches from E4S. And so this speeds up the installation. This is a project that's primarily targeting the Summit system at Oak Ridge National Labs. And as you're probably well aware, that it's a Power 9 system with V100 GPUs from NVIDIA. So having a way to install this package very easily using E4S is a great boost to their productivity. I also mentioned earlier that it's not enough to just put together binaries of these packages. We must run a validation test suite to verify that the package is doing what it claims to do. And to do that, we have this E4S project test suite. And this is, of course, a work in progress. And we are adding more and more test cases. Here you can see a test case for a package called Magma. And in each directory, we have a clean.sh, there's a readme, there's a compile.sh, there's a run.sh, and also a setup.sh. So it's easy to follow those things and then launch the test cases and sweep through an entire installation, whether it's a container-based installation or a bare metal, where you can point to the Spack, and then you can just say, please run these test cases. And for each test case, it goes in recursively, it goes and cleans it up, it sets it up, it compiles, runs, and so on. So we can have reproducible container builds using these base images from E4S. And we have this build cache that can help with the creation of these images. Here are some runner images for GitLab. And continuous integration is an important part of our strategy. Here are builds that you can see in progress for E4S, where we are building on multiple architectures, different operating systems. And we have a number of different platforms that are used for this deployment. This is a snapshot from our gitlab.4s.io project. We have these build pipelines not only at the University of Oregon, but also many of the DOE labs. This is the build pipeline on Cori at NERSC. And then there is a GitLab build pipeline at Oak Ridge National Labs on a machine called Ascent. This is a small scale system that's trying to mirror Summit. And it allows the facility to build a whole stack of software locally using the compilers and MPI that are relevant to their facility. So we also have a doc portal. And this is a project that aims to provide a single online location for accurate product descriptions. Now we realize that we can put up a web page, and very soon it will have a list of packages that provide some input, but you need to constantly update that. And we realize that the most current information for some of these open source packages resides in their own GitHub websites. So we rate these websites and pull in the latest information. And then there's a directory which allows you to map the files. So you can say, here is the license file, here is the README file, this is the installation instructions or the change log. And we can rate these repos. We can show a custom web page like this. So there is some summary information about the name, functional area, description, license, and also when they had updated this. So you can search for a package, you can look at the area, the description, and then you can click on it. You can see the summaries, even the badges, and it goes to the original package page. So you can follow that. So it's a single portal that allows you to track all of these different products. We have a virtual box image. And as I mentioned earlier, this is an image that allows you to get familiar with container runtimes. Now, container technology is new for a lot of people, but it holds a lot of promise. You can learn more about Docker, Singularity, Shifter, and Charlie Cloud runtimes using a single virtual box image on your laptop. Now, with this, there's an important issue about MPI. Internode parallelism is dominated by MPI runtimes. Whether you have MPH or you have OpenMPI, and you may be using a container. You may be using, say, a Singularity container that has MPH in it. And you have multiple libraries like HDF5, Tyrino, Spec, all configured with that MPI. So if your application, which resides outside of the container image in your home directory, that is built using the libraries that come from the container, then how do you launch such an MPI application? Do you use the MPI within the container? And then is it restricted to a single node? What do you do about inter-node executions? Now, we have network interfaces that are very advanced and are used effectively using the system MPIs. You may have OpenMPI or some variant of MPIG that is used for an MPI that's available on your HPC stack. So we have a tool called E4S Container Launch Tool, or E4S-CL, that helps simplify the launch of MPI jobs. And you can use this with Singularity right now, and we are moving towards Shifter as well, supporting that. And it has a very easy syntax. You just say, initialize it with the backend of Singularity. You give a startup.sh script where you can say that once the container is launched, you should load these packages. Like there could be a package such as, a command such as Spack load Trilinos or Spack load HDF5. And then it will load those commands from the shell script. And then you can specify your image. With this, it finds out the libraries that are needed for the MPI substitution. It keeps it in a small database. And when you run your MPI command, it could be an MPI run command like this, but you prefix it with the E4S CL. And then you will be able to just launch that application, but substitute the MPI on your HPC system with the MPI in that image. And this is a very interesting project. You can learn more about it. It's all open source, MIT style license. You can download it from this GitHub site. And this is the architecture of E4S CL, where it has to figure out which libraries to substitute, how to change the launch command so that you don't have to struggle with specifying arcane LD preload instructions or some MPI commands. So in summary, I would like to say that E4S is not a closed system that's based on DOE software development teams. You should think of E4S as an extensible open architecture software ecosystem that accepts contributions from US and international teams once they accept the policies, the community policies that have been developed. You can think of it as a framework for collaborative open source product integration, a full collection of compatible software capabilities, and a manifest of a la carte selectable software capabilities. I think of it as a vehicle for delivering high quality reusable software products in collaboration with others, and a conduit for future leading edge HPC software, targeting scalable next generation computing platforms. A lot of this work goes on at the Performance Research Laboratory at the University of Oregon that I direct. You can learn more about it from the University of Oregon webpage. This is our campus in Eugene. And I would like to thank the Exascale Computing Project for sponsoring the E4S project. So with this, I'll take any questions. Let me just go to the chat window and see if anyone has questions. Let me just repeat the URL for the slides if you would like to download these slides. Any questions so far? You can feel free to unmute yourself and ask.
Yes,
we
so
still have about 5 minutes.
Like Samir said, you can unmute now and ask your question. If you prefer to chat it, that's also fine.
And if not, you should feel free to contact me over email if you have any questions about this. Here is my email address. And this is the URL in case you did see this. If you just joined later, you can download the slides from this location. I hope you find the extreme scale scientific software stack useful in your work on OpenPOWER systems. I hope you have a good conference.